So I guess I'll start. So problem one for today is called longest consecutive sequence. Let's just go through the problem statement once. You're given an unsorted array or list of integers, n integers, which is called R. Your task is to return the length of the longest consecutive sequence. So we can understand this problem statement better by going through the example given over here. We've been given an array of elements 9, 5, 4, 9, 10, 10, 6. And we need to find the longest consecutive sequence in this array. So by looking at the array, it's a small test case. We can tell what the longest consecutive sequence is. 4, 5, and 6, of course. They are consecutive numbers. They lie within the array. So that is our answer. We'll output 3 because the length is 3. So we'll go over 3 approaches for this problem. The first approach is the brute force approach, like the most naive approach. While looking at the problem only, we can think of this approach, and that approach is the linear search approach. So what we can do in this approach is for every element in the array, we can linear search for the next consecutive elements we want to find. So I'll go through a dry run of this so you can understand it better. If an interviewer asks a problem or DSA problem to you in the interview, you always give the dry run or the brute force approach first, and then you give him the optimal approach because he always wants to see your reasoning. So let's just start with the brute force approach, linear search for every element. So first, of course, we start with the first element in the array, which is 9. And now we linear search for its consecutive numbers. We'll take 9 as the start of a sequence. And now if we want consecutive sequences, we'll need the numbers 10, 11, etc. Right? So we'll just perform a linear search through the remaining of the array to find first the number 10. I'll check. Okay, I found the number 10. So I'll increment my count to 2. And now I'll start searching at the start, my max will be 1, of course. And then I'll start searching for 11. 11 does not exist in the array. So I'll update my max. My new max will now be 2. And now I'll perform the same process for 5. If I do it for 5, I'll first look for 6, which does exist in the array as we can see. So my count will now be 2. And now I'll search for 7. Does 7 exist in my array? No, it does not. So we'll again try and update max. But since max is also 2 and account is also 2, there's no updating taking place. So we'll move on to the next element. We set count to 1 again. And now we search. What is the next element to 4? It's 5. It's there in the array. We can increment a count to 2. Now we'll search for 6. Does 6 exist? Of course, it does exist in the array, the last element. Our count is now 3. We'll search for 7. 7, as we saw before, does not exist in the array. And now again, we'll update max. New max now becomes 3. And now if you iterate through the rest of the array, you will find that you won't really get a better maximum. A maximum length of a consecutive sequence will be 3 for this array, as we found. So this is the brute force approach. Very, very easy to understand, but it is equally as slow. This algorithm will have a worst case time complexity of big O of n square. That means for every element we are searching the array, the entire array once, in the worst case, of course, that is. So that if there are n elements and for each element we are searching it n times, it would take order of n square operations. And if we take a look at the constraints over here, it is given that the constraints are 10 raised to 5. So that would take 10 raised to 10 operations or around 100 seconds. That is really, really slow. And the interviewer will, of course, ask you for a better solution. Over here, if you take a look also, the time limit is mentioned as 1 second. And this algorithm will take around 100 seconds to run. So it is not really feasible. So does anyone have any doubts in the brute force approach? Why we don't use it? How did I get the time complexity? Anything else? If not, then I'll move on to the second. Approach. The second approach is sorting and searching. So what was the worst part about the brute force approach? What was the redundancy? You might have noticed that while I was making checks, I performed a lot of repetitive checks. If I had already checked for 4, like 4, 5, 6, then no need to check for 5 again, right? If 4 exists in the array, the longest subsequence will start from 4. It will never start from 5, right? Because 4 comes before 5, and in any subsequence where 5 is present, 4 will also be present. So there's no real point in checking for 5. And again, no point for checking for 6. If you're checking for 9, why would we check for 10 again? So how do we eliminate those useless iterations? How do we eliminate those useless operations? So for that, we can use sorting. So we can initially sort. I've taken the same test case for a dry run to give you a better idea of what is going on. Let's just perform a dry run. Of course, this is a sorted array. You can use the C++ sort function. It'll sort your array for you in n log of n, of course. And we'll start at the first element again. We'll check, okay, is the next element uh, a successor to the current element? So if we have 4, we need the next consecutive element, right? So we need 5. It is indeed 5. So we can implement count, we can increase count to 2. And of course, let me just set my max over here to 1, because of course max can't really be less than 1 unless our array is empty. So for I start with 4, I check that the next element is indeed 5. So I can increment my count. I'll check again. Now for 5, is the next element 6? It indeed is 6. So I can increment my count again. And now I'll check for the next element. Is it 7? Because to be a consecutive subarray, it should be 7, right? But it isn't. So it's 9. So I'll increment my max to 3, and I'll reset my count to 1, and I'll begin performing the operations. Now I have 9 over here, and the next element is also 9. What do you think I should do in this case? I can simply skip this, right? Because 9, they mentioned in the question, it should be a consecutive subsequence. It does not matter if there are duplicates and all. I can simply not consider this 9. I can move on to the 10. So I'll skip. If you're wondering how do I implement this, you can just run a check. If vi plus 1 equals to vi, then just continue. Because this element is again redundant, no need to check for this. We can move on to 10, a count will get incremented to 2, and we'll reach the end of the array, and a max still remains 3. So as you can see, this approach works too. What will be the time complexity of this approach? Would anyone want to try? So the time complexity of this would be a worst case time complexity of big O of n log n. Why n log n? That is mainly because of this sorting function only. Completely actually because of this sorting function. The searching part means iterating through this array. You might have noticed I only pass through the entire array once, right? So if I had n elements, I would only pass through the array once. That is n times. So that doesn't really take up much of the time. The majority of the time is taken up by sorting, which is n log of n. You can't sort faster than n log of n. So that is the worst case time complexity of this code. And now let's go on to the optimal solution. If you notice in the question, they've asked us to solve this in O of n time complexity and O of n space complexity. Now, the first two solutions I mentioned were using constant extra space. That means I was not declaring another data structure, an array to store elements in it, just a couple of variables like max and count. I wasn't really using a lot of space. But a common theme in programming is if you want to reduce the amount of time your code takes to run, you always have to give in more space. It's a trade-off between time and space always. And in this question too, we can bring down our worst case time complexity of O of n log of n down to O of n by increasing the amount of space used. So like we made an observation in the first one, we can make an observation in the second one too, right? We notice that duplicate elements don't really make a difference to us. So we can cut down on that. So we need a data structure which does not have duplicates in it. as well as for it to be constant time, we'll always have to pass through the entire list once, correct? We cannot really count all the longest consecutive subsequence without passing through all the elements once. And a maximum is also O of n, as mentioned in the follow-up question, right? We need a worst case time complexity of O of n. This is only possible if our data structure allows constant time lookup and constant time insertion. What are some of the data structures you know which have this property? Of course, one of them are vectors or arrays or whatever. You can insert into an array in constant time, as well as you can access an element in constant time. If you say array of I equals to phi, that is insertion in constant time. And if you just want the element, you can do array of I. And these take constant time. But we can't really use an array because they've already given us in the form of an array. And how do we eliminate elements? The first two cases we saw, we either need to sort it, which takes more time, or we have to run two for loops, which would be even worse. So we can do this using a data structure called an unordered set in C++. What is an unordered set? An unordered set is a data structure that stores distinct elements and allows constant time insertion as well as lookup. So what is the benefit in this? So just as I mentioned in approach 2, I'll need to look at the first element in the starting element of a subsequence, right? The internal elements don't really matter to me because I know if there is no point checking from 5 onwards if I can check from 4 onwards, because the subsequence which contains 5 should also contain 4, and the subsequence which contains 4 will always be better than the subsequence that contains 5. So for that, I can store it in an unordered set. In my unordered set, I'll explain to you with the help of the code only. You will understand it better that way. So I declare an unordered set S and I fill in the elements of the array. This is a way you can do it in C++. You can give the iterator to a start of the vector and the end of the vector, and it will automatically create your set for you. I'll initialize my max to 0, like my current maximum to 0. It can be -1 or whatever. It'll be incremented later anyway. Don't set it to a higher number. In case your max ends up being 1 or 2, it will give you a wrong answer. So -1, 0, 1, those should be fine. Not a higher number though. So I'll iterate through every element in this set and I'll check if it is the starting element of the set or not. How do I know if it's the starting element of a subsequence or not? I check if a previous number exists or not. Let me go back to this. If I start with 9, is it a starting element of a subsequence? How do I check for this? Is there 8 present in the set? There isn't an 8 present in the set, so 9 will be the starting point of a subsequence. So I can start with 9. I'll start with 9. I'll set my count to 1. And now I'll need to look for 10, 11, 12, till wherever the consecutive sequence ends, right? I need to find the longest consecutive subsequence. So I'll keep moving ahead and ahead. If I start with 9, I'll check for 10. If 10 exists, I'll check for 11, and so on. So I do that with the help of a while loop. I set my x to I plus 1 because I already have I. I know my count is 1. And I'll check. So suppose my I is 9 over here, right? My I is 9. I'll start looking for 10. I'll use the find function if it's not equal to end. So the property with sets, a lot of you all might already know, is that if the element does not exist, it'll return an iterator that points to the end of the set. If the element exists, it'll return an iterator pointing to that element. So this basically checks if the element exists or not. If the element does exist, the while loop code will execute. It'll increment x. X is, of course, the element we are checking for. So if originally I was 9, right? We checked for 10. If 10 exists, we'll now want to check for 11. So we'll increment x. And since the element was found, we'll increment count 2. And this will keep going on and on until we do not find the next element we needed to find. In this case, we'll stop after 10 because when we try to check for 11, we'll find it does not exist. and we'll simply update a max. But suppose there was 11, there was 12, it would go on and on until it would reach an element we did not find. So this for loop would execute, and at the end, we would simply return a maximum. Notice you're updating a maximum after every iteration. So yeah, that was the code. It takes O of n time complexity because it's a single for loop. All of these operations are constant time. You might be thinking, okay, there's a for loop outside, there's a while loop inside. What do I do in that scenario? But notice that maximum number of elements will be checked will be big O of n only, because we are only executing all of the code inside if the element is at the start of a sequence, and if it is start of a sequence, the remaining sequence gets handled over here only. So it is of the time complexity big O of n. Space complexity is also big O of n because we are using an extra set, right, which will contain in the worst case n elements if all the elements in the given array are distinct. A set filters out duplicate elements. So that was the solution for problem 1. We learned about unordered sets. We saw a couple of approaches, time and space trade-off. Does anyone have any doubts? Okay, so we'll move on to problem 2 then. So problem 2, how many of you all have tried problem 2 today? It was longest subarray zero sum. Any approach? Did you all try it? Did you all get an error? Did you all get an TLE? Did you all think about the logic of the problem? Okay, so for time complexity, we sent some resources on the group. We'll resend it to you. Time complexity is basically a measure of the worst case time, worst case number of operations your code will execute in as a function of the input size. So if your input size is n, how much time will your code take to run? So there are various time complexities. Suppose there's big O of n. That means for n elements, there are n operations performed. If your time complexity is O of n square, then then for n elements, there will be n square operations performed. Suppose your input size is 100. If your code had a time complexity of big O of n, it would take approximately 100 operations. And if it had O of n square time complexity, it would take around 10,000 operations. This is very, very important for very, very large inputs, very, very large test cases, because in the real world, you'll never get test cases which are very, very small, right? They'll always be in the millions or billions. Suppose you're performing a Google search, and your Google search returns 10 billion results. If Google had an algorithm that took O of n squared time to execute, it would probably, the universe would probably end before you got your search result back, right? So it is very important to have faster algorithms, and the speed of algorithms is measured in big O of n notation. We'll resend the resources on the group. You can go through them and you'll get a hang of it. Does anyone else have any doubts? Okay, so then we'll move on to problem 2. Problem 2 for today is called longest subarray zero sum. What does this problem want from us? What have they asked from us in this problem? So in short, we have to find the length of the longest subarray whose sum is 0. So suppose we have an array. Let me just write something over here. A subarray, does everyone know what a subarray is? A subarray is a contiguous set of elements in an array. So suppose my array is 1, 2, 3, 4, 5. 1 would be a subarray, 1, 2 would be a subarray, 1, 2, 3 would be an subarray. Like also, you could start from any index. 2, 3 would be a subarray, 3, 4, 5 could be a subarray. Basically, continuous elements. You can't take 1, 3, and 5 and call that a subarray. That is not a subarray, that is a subsequence. knowing subarrays and subsequences are very, very important. You might have noticed through these past 2 weeks, subarrays and subsequences were mentioned a lot. And yeah, so a subarray is a contiguous set of elements. So they've asked us for the length of the longest subarray whose sum is 0. Let's do the same thing as we did in the last problem. Let's start with the brute force approach. Does anyone have any ideas on what the brute force approach for this would be? Taking inspiration from the previous problem, maybe if you solved this kind of problem before, a lot of you might have solved problems involving subsequences, right? So how would you go about this problem? Forget about the constraints for a second. Just this problem, very small constraints. You were asked to solve this in your programming test or whatever in college. How would you go about doing this? So the brute force approach for subarray problems are always generating the subarrays and generating all the subarrays and then checking if they match your required case or not. So that would just simply indicate running two for loops, and for int I equals to 0, for example, and for int j equals to I plus 1. And thus you generate all your subarrays. You can simply find all the elements within your subarray, the sum of the elements, check whether they are equal to 0 or not. If they are 0, you can check if you can output the maximum length of your 0 sum subarrays. That's what the question wants from you. But okay, can anyone tell me the time complexity of this approach? It has one for loop inside another for loop, and on the worst case, that would take how many operations? Anyone? That would take big O of n square time complexity, because for each of the elements in the original array, you're checking n other elements on average. It's actually not exactly n square, it's a little less than that, but we always take the highest term as a worst case time complexity. So if we look at the constraints, again, they are 10 raised to 4, and this wouldn't really work. O of n square wouldn't really work over here. So we need a better approach. They haven't really mentioned anything over here. You could try submitting an O of n square, you would get a time limit exceeded. So what would we do in this kind of problem? So the prerequisite for this problem is the concept of prefix sum. What is a prefix sum now? A prefix sum is the sum of the prefix sum of an element in a vector or in an array is the sum of all the elements that occur before it and the element itself. So I'll take an example using this array. What will be the prefix sum for index 0, that is element 2? It would be 2. For minus 3, it would be 2 plus minus 3. So that will be minus 1. For 4, it would be 2 plus minus 3 plus 4. That would be 3. For minus 2, it would be 1, 2. Then for this one, it would be 3. And for this 3, it would be 6. So let me just space this out evenly. So this would be the prefix sum. Of course, you do not need to actually calculate manually for each and every element the sum of all the elements before it. The shortcut formula for prefix sum is simply, suppose I'm storing all my prefix sums in a vector or an array called prefix. Prefix of I equals to prefix of I minus 1 plus A of I. If this array was I, then the prefix of a random element I would be the sum of the prefix of the previous element plus the element itself. Does this make sense to you all? Because prefix is nothing but the sum of all the previous elements, right? And there's no point recomputing over them over and over again if you already computed them and stored them somewhere. So a prefix sum of a particular element in an array is simply the prefix sum of the element before it plus that element itself. That is a very, very important concept to keep in mind. Why would we require prefix sums in this problem though? So notice a subarray can only be zero if in a given array we have two elements which have the same prefix sum. What do I mean by this? So suppose my I've taken this entire subarray and I want to find the subarray in this which adds up to zero. How would I do that by only knowing the prefix sums? Could I do this? Suppose you didn't have this information. By the prefix sums, is there any way for me to find out which subarray in the original array has elements equal to zero, sum of elements equal to zero? I can do this if the prefix sums in are equal to each other, right? If my prefix sum over here is 3 and my prefix sum over here is 3, that means whatever elements which are getting added or subtracted in between those two prefix sums have a grand total of 0. Suppose I take x, a number x, and I add 5, I subtract 3, I perform n operations. And after performing those n operations, my final value is also x. Then isn't that not the same as just adding 0? That means the sum of all the operations I performed was just 0, right? Because I started also with the same number, I ended also with the same number. That is only possible if all the operations cancel out each other, or in this case, all the elements add and subtract to form 0. So we can make use of this concept to speed up our computation to save time. We'll be making use of the map data structure to store our prefix sums, because we need to know which index the prefix sum occurred at, right? Because they've asked for the maximum length. Over here, suppose I'm finding the prefix by looking at the prefix sum, I can say, okay, at 2 over here, I have 2 over here too. So my length would be what? This would be index 0, this would be index 4. So my length would be 4 elements. And I can verify that in my original array too. -3 plus 4 is 1. 1 minus 2 is -1. And 1 plus 1, -1 plus 1 is 0. So this subarray satisfies the question's condition. A subarray with sum 0. And the length of this is 4, which I can get by subtracting this index from this index, right? So the index where I got my prefix sums as same values. So I'll make use of my map data structure, and the pseudocode or the intuition for this is really simple. I'll go on computing the prefix sums for each and every element. I'll start a for loop. From the first element, I'll compute the prefix sum. I'll check, does that prefix sum already exist in my map? If it does not, I'll add it to my map. So I'll add my prefix sum as the key, and the value will be the index at which it occurred. So key value pair is the prefix sum and the index. If it does not exist in my map currently, I'll add it. And if I reach a prefix sum and it does exist in my map, I can say that between these two indices, my subarray is 0. The sum of all the elements in the subarray is 0. And I'll check, is this better than the answer I already have? If it is, I'll update it. Otherwise, I'll move on. That is a very simple pseudocode for this problem. I'll go through a dry run with this test case to help you understand better. What was the step I said? Iterate through the entire subarray and calculate or find the prefix sum. Prefix sum for 1 is 1. Does it exist in my map? My map is currently empty, so it does not. So I'll store it in my map. Prefix sum of 1 occurred at index 0. Over here, let me just create something for you to help keep track of the current maximum. I'll set my current maximum as 0 for now. And over here, my prefix sum for the next element, that is 2, will be 3, right? Does 3 exist in my map? No. So I'll set it over here. I got a prefix sum of 3 at index 1. I'll go to -2. What is my prefix sum over here now? It is 1. And did I get 1 before? Yes, I did get 1 before. As I've indicated in my map, I'll perform a query on my map. It'll give me the index. So what did I say? current index minus index of where I got the prefix sum before. That was index 0. So index 2 minus index 0, that's 2. Is that better than the current value I have? It is. So I will store that over here. I'll move on then. I'll move on to 4. So what is the prefix sum till 4? The prefix sum till 4 is 5, right? 1 plus 4. As I said, prefix of I equals to prefix of I minus 1 plus ai. So the prefix of a current element is the sum of the prefix of the previous element plus the element itself. Does 5 exist in my map? No. So I'll set my index. It's an index 3. Of course, in all of these questions, assume zero-based indexing. So it does not exist. I've added it. I move on. -4. My prefix is again 1. Have I encountered 1 before? Yes, I have encountered 1 before on 2 separate occasions. But of course, it is the most beneficial to me to take the first occurrence, right? Because I want the longest. If they'd asked for the shortest, it would be a different scenario. But they've asked for the longest. So I'll always take the first occurrence of that element. It's 1. It occurred at index 0 as I stored in my map. And now I'll calculate the length. Index of the current prefix is 4. Index of the first occurrence of this prefix is 0. 4 minus 0 is 4. And I'll update my max to 4. So that is it. There's one simple test case that you need to keep track of too. Suppose I had a -1 over here too. Then what would my answer be? Would my answer still be -1? Over here, I would simply take -1. Means my prefix would be 0, 1 minus 1, 0. And I would check, is it in my map? No. Then I would simply add it to my map and move on. But this would give me an incorrect answer, right? Because in this case, the entire array is a array with some 0, right? So this should also be considered. So I'll add a special check for that. As you can see in the code, if current equals to 0, answer is equal to max ans I plus 1. So basically, this is the same code for that. Basically, I'm saying the entire array till now has been an array with some 0. So I'll set my answer to that. This code does exactly what I've described. It is a map of integer to integer. I've called it MP. 2 variables, answer to keep track of my final answer. Current is the current prefix sum. And for my boundary condition for my for loop, I iterate over every element. I find the prefix sum for the current element, which is simply equal to the previous prefix sum plus the current element. I check, does it exist in my map or does it not? In this case, it does not exist. It does exist in my map. Because the pointer is not equal to the end pointer. I do what I say. Answer equals to max of answer and current index minus the index at which the prefix sum occurred before. Otherwise, I'll simply add this key value pair of prefix and index to the map. And this will go on and on for every iteration. And finally, at the end, I'll return my answer. So that was problem 2. This has a time complexity of O of n log n, a for loop, and searching for anything or insertion into a map takes like O of log n, like, yes. So that was problem 2 for today. Does anyone have any doubts? Prefix sum is a really important concept. It helps you save time by pre-computation or other methods. It's used in a lot of problems. So those are the 2 problems for today. If anyone still has any doubts, they can post them in the group. The Big O Club is always open for discussion. Today's doubts, any other day's doubts, please do post them on the group. I'll be posting the solutions in just a couple of minutes. Go through them. Try resubmitting the problem on your own, coding it out again. That's all for today. Week 2, day 4. See you all tomorrow. Thank you for attending. Bye-bye.